you are able to do it with low-cost hardware. So we're going to show you how, and we're hopefully going to have fun doing it. So hi, this is indeed, I'm Alyssa, this is Albert, and all you need to know about us is I'm a PhD student, and Albert is, I think, a freelancer, he calls himself. And what this means is you need to know two things about us, one of which is we're cheap. So I'm a PhD student, I don't have much income, and Albert is, well, be realistic, unemployed, so he doesn't have much money. And we're lazy because, I mean, I'm a PhD student, it's more, I'm super, super busy and I have no time, and Albert is just plain lazy. So cheap and lazy, and that's kind of going to be the focus of this talk. Even if, you know, you don't have much money and you don't really want to put too much time in, you can still have at least fun doing this and understanding these attacks. So as I said, we're going to talk about side channel analysis today, and we're going to talk about how to do it with cheap hardware. We're going to give some demos. We're going to actually do it here on stage a bit. And at the end, because we like fault injection, we're also going to show you a little bit of fault injection just to finish off the day. So side channel analysis, there's a lot of maths, there's a lot of theory. So it's kind of hands up if you have some vague idea about the math, the theory behind side channel analysis. Okay, well, you know, you don't qualify to be here. The talk abstract clearly said you need a healthy dose of ignorance, and that's really what we're looking for today. So please don't cry too much when we don't discuss the math and we don't really go into the theory. This is going to be kind of a, we're going to tell you how it works, but then at some point it's going to be magic, but you don't need to care. So kind of a high-level overview just to what on earth are we talking about? What are we going to be discussing today? So the idea is we have some kind of target. We'll talk about what kind of target in a second, but you have something with a computer, a CPU, some microprocessor. And you have an attacker that has some kind of physical access to this. Because today we're going to be talking about power side channels. You need to be able to measure the power somehow, and we're going to assume you're actually going to be doing this by physically poking at the device. And you need some way to send the device some commands, because you want to have some control over what you're telling it to do. Because we want to keep our life simple, we're lazy, we want this to be direct, we send it a command, it does something. At the bottom, we have this power trace, and this kind of tells us what it's doing. And the usual context for this historically is smart cards, these really secure devices, secure elements nowadays, which are really designed slowly to actually nowadays resist this kind of attack. And this has become more and more relevant for various other targets. In fact, you have these systems in cars to protect crypto keys. If you saw the keynote talking about these keys, which are used for vehicle-to-vehicle communication, those are going to be in secure elements, are going to be locked away from you. But also often just it's interesting in the general context of Internet of Things, of random devices, because everything has information you want to get out of these devices. Discuss in a second. But when I say Internet of Things, what I mean is my teddy bear. So this actually is another device you can do side channel analysis on. I found this at the supermarket. It cost me €5. It's cuddly, which I was really surprised at. So it's actually huggable. But you can also do side channel analysis attacks on this guy. Unfortunately, he didn't fit in my luggage. Another time, maybe. So first, I'm going to talk about why you should care about this, because it's kind of side channel analysis. It's been typically on kind of these really sophisticated, secure devices. But actually, side channels in general, and that includes power side channels, they're really useful when you're stuck. So if you're trying to exploit a device, but you don't really know what's going on inside, maybe you don't have the firmware, you know, maybe you just, something weird is going on, and you don't have any insight into the device. And what we're going to show you is side channels can be used to basically gain some extra information about what's going on, to gain some just insight into what's happening. And this is kind of smart card stuff again. The standard example is this pin check, and I'm going to use it because I think it's really nice. You have maybe a 4-digit pin in, say, a credit card or any kind of secure system. And it has some kind of loop like this, which checks, is the user input, the command you sent it, maybe over serial, equal to the secret pin. And if it doesn't match on one of the loop iterations, then it fails out. So it's just 1, 2, 3, 4, checks if they're the same. And this is a power trace from a device running this kind of pin check. And you look at this and, yeah, I have no idea what's going on in this thing. But I can tell you, keep an eye on this little circled bit here. This is just a random pin we've sent to the device. What I'm going to do now is replace this power trace with a trace we've taken where the first digit of the pin is correct. And you can see, okay, the pattern kind of changed there. Specifically, what happened is now we have 2 of these patterns when we had 1 before, because we have 2 loop iterations, and this little pattern is representing one of these iterations around the loop, doing a pin check. It's gone from 1 to 2. If I put them side by side, if we have no digits correct, you get the first one. 1 digit correct, you get the second one. So just literally by looking at this visually, by just looking at the power trace and seeing, oh, when I send this input, wow, it changes, you can actually gain information about what's going on. And I think this I would recommend to everyone, because when you're stuck, when you don't know what's going on, and you're trying to even debug your device, it can be useful. But then, let's step back a bit. It's like, wait a minute, how on earth do we do this power measurement in the first place? So we have some kind of processor, some kind of CPU, and we want to get the power measurements, and we're going to do that using an oscilloscope. How do we do this measurement? Well, okay, you have a power line, so it's got to be pulling this power that it's using from somewhere. We want to measure how much power it's using to get these pretty graphs. So what we can do, we just cut the power line, and ideally, we just take an oscilloscope, and we just plug kind of one end into one side, put another probe or the earth clip into the other side, and just measure the power. And it's almost that simple. What you have to do is, you can't do this directly, but what you can do is we put a resistor in there, called a shunt resistor, and it's just a matter of experimentation. So you just have to pick a resistor that has a high enough value, a low enough value that it still works, but a high enough value that the measurements work. But you just kind of fiddle until you have something that works. And then you just plug your oscilloscope into either side. And this is what we're going to be doing today. And it's just kind of, okay, this is all very theoretical so far. We want something you can go and do at home. We want something that everyone can do at home. And so as an example target, we picked the Arduino Nano, which is perfect for many reasons. It's cheap. Ideally, everyone has them lying around, or people you know have them lying around, and they're not going to notice if you run off with them, though they will notice when you see what you do to them. And it's not secure, which is really great because it doesn't have any protection whatsoever. And no matter how much you screw up, believe me, you'll see some examples later, you will manage to do side channel analysis on this kind of device. The bad news is that in practice, making these power cuts is not so simple. For example, on the Arduino Nano, the communication is done via a serial to USB communication chip. And the power that it's using, you don't want to mess with. And so you actually have to make cuts in 2 places to preserve the power, do a bit of soldering. And in real life, I think the most difficult part, at least for me, about doing side channel analysis is this, is getting things soldered and quickly piling on hot glue. I think these are all Alberts, which I can tell because they all work, just so that they actually, so that you actually have all of these bits wired in the right place, and you have headers that you could connect your resistors to. I mean, if you get this far, and if you just, so you've made your cut here, so you have little headers sticking out the side, your power in, a header somewhere else, your power out. If you could connect the 2 of those with a wire and your device still works, then you're 90% of the way there. And the great thing about the Arduino Nano is even if you screw up a whole bunch of them, it doesn't matter because they're cheap and they're plentiful and you can play with them. So again, I really recommend that if you get a chance, play with this. If you're, crazy enough to enjoy this kind of thing, but you should. So going back to the big picture. So when you actually do side channel analysis, you're going to have your target, some kind of processor. You're going to have made this power cut, so your signal is going to be a power signal. You're going to connect this to an oscilloscope. You're going to have something called a trigger, which if you're not familiar with oscilloscopes, tells the oscilloscope when to start measuring. And then you're going to have some kind of computer which is sending these commands, telling this target, please do some kind of operation, maybe giving it pin codes. And the PC is going to be collecting the measurements from the PC, from the oscilloscope. The great news is it can be a really cheap PC, which if you're plugging things into kind of handmade hardware where you solder things together is great, because you probably don't want to be doing this to your very expensive laptop. Although, having said that, I have a very expensive laptop right here, and it's not broken no matter what I've done to it so far. So, okay, we're going to do a demo in the sense that right in front of me, we have a setup, which you probably can't see very well, which is unfortunate. I will show you once we've actually done it. But basically, what I have here is I have a modified Nano, and I have a bunch of resistors, and I have an oscilloscope. And so what I'm going to do is exactly as described in this slide here. What I'm going to do, I'm going to communicate with the target and send it some signals, and then I'm going to look at the signal I get from my oscilloscope. And the oscilloscope is communicating via USB. So this is just a Python script, which I hope will actually communicate with the target. If not, I have to replug things. There we go, it's doing something. And then I have a very quickly hacked together user interface, which just shows signals from the oscilloscope. So you can see some kind of pattern here. And if I just keep on pressing get, then sometimes you get real noise like this, which means we're not capturing anything interesting. Probably the device isn't doing something. But you also get really nice signals like this, where you can see, wow, there's real patterns here. And this is actually, you can really see what's going on, as we'll explain.
Alexa, you can switch actually to the camera.
Awesome. Do you know how?
Yeah, just push the button.
Is there a button here?
This one.
No, the right one, yes.
Oh.
Now it should switch. Hopefully.
Awesome. Not that, of course, you can see this very well, but okay, we've shown the user interface. So what I'm actually going to do here is just hopefully kill this and simply hold things up to the camera. It's I'm going to terribly regret this, aren't I? But so this is which you can't see very well in the lighting. But yeah, take my word for it, this is our mangled together Arduino Nano. Still plugged into power, you have this little red LED, which is very misleading because the LED is powered directly from the USB power and not from your power cut. So you see this red light and you think, oh, it's working, but no, you screwed up the power cut. And then you have all of this hot glue on the back that you can't really see. And because I like easy to see things, I've mounted all the resistors here just on this big board. We'll talk more about this later. For now, maybe go back to the explanations. Am I going in the right direction? Yes, I am. Okay, so to talk about what's going on. So we saw, just quickly hitting the button there, collecting data from the oscilloscope, we saw lovely patterns like this. And what exactly does this mean? Why do we care about the power usage of the processor, of whatever's running on the Nano? And to cut kind of a long story short, for our purposes, we're going to be talking about software. And what we're seeing is the switching of the transistors in the device. And the important thing is that the power usage of these transistors depends on the data being processed and the code being run, but we care today about the data being processed. And for software, it turns out the power usage is higher the more ones in your data. It's all binary. The more ones in your data, the power usage is higher. So just to make it easier to discuss this stuff, there's something called Hamming weight. If you're not familiar, the Hamming weight of a byte, for example, is just the number of ones which are set in that byte. So 0 has a Hamming weight of 0, and FF, you have all the ones set, has a Hamming weight of 8. But this is not so perfect for working out what's going on, because, for example, the number 5 has 2 ones in binary, Hamming weight of 2, but 0x11 also a Hamming weight of 2. So whatever we're going to do for side channel analysis, if we're going to depend on this switching, then we're going to have to find a way that works, even though all we can really see is the Hamming weight of these values being processed. So just to kind of, again, step back a bit, how can we be sure this is what's going on? Well, you can try this yourself. You just send a bunch of random bytes. You do some calculation on, say, the Arduino Nano with those random bytes, and you take power traces. And you say, okay, we take all the power traces which are processing data with a Hamming weight of 0. Does that look different to when we're processing data with a Hamming weight of 1 or 2? And if you graph this, then you can see that, yes, it does actually make a difference. So we average the data with Hamming weight 0, Hamming weight of 1, and so forth. And you can see you actually get 8 different levels here. Okay, it's not so easy to see with the eye because there's lots of other things going on in processors, but you can definitely see this from software. And to cut a long story short, what we're actually going to do today is talk about how to steal encryption keys. This is the traditional use of side channel analysis, and it's because keys are awesome. So keys, they might be used to protect firmware. They might be used to protect communication with a backend. They're used for a lot of useful things, and if you want to compromise some kind of IoT device, then often having these keys is really important, especially for firmware. If you can get these keys used to decrypt your firmware, then you can look at the firmware, you can find vulnerabilities, and you can exploit the software. But if you have no idea what's going on, yeah, sure, side channel analysis will give you some insight, but you're probably not going to have much luck in a reasonable amount of time. And what are we going to do? We're going to look at AES because it's actually secure. It's what's used in the real world. It's pretty much unbroken unless you have side channels or fault injection, which is why these things are fun. And AES is made up of all of these different rounds. It's complicated how many rounds there are. I will say 9, maybe 10. But actually, today, we're only interested in the very start here. But the reason it's interesting to know there are all these rounds is this pattern that we saw earlier with all of these little spikes, which you got from our oscilloscope in our demo here. Actually, each of these is an AES round. And the reason I'm saying it's complicated is because not all rounds of AES are kind of equal. You have kind of an initial and an end round. If you count the peaks here and you count the dips, you get different numbers, 9 or 10. But the great news is we also don't really care about which round is where, other than that, first of all, it gives a great pattern. This is really easy to spot on the oscilloscope. So if you're trying to work out where is the AES happening, if it's software AES, it's where you see this pattern. And we only care about the start. So if we kind of zoom in to the start, what happens at the start of AES? Well, for byte 1, there's this stage called key addition, where you do an exclusive OR of the first byte of the incoming data with the first byte of the encryption key. And then we go through an S box. For the second byte, we do key addition with the second byte of the key, and then we go through an S box. And the great news is, for this stage, that means that we can look at it byte by byte. So if we're looking at the first byte of the input, and remember, we control the input because you can send commands, for example, if you can control the encryption or decryption on the device. If it's firmware, then you can simply set the firmware on the device. You can reflash it to be whatever firmware you want, set it upgrade images. You control the input. And the key byte being used is the one corresponding to the input. So the first byte of the input is the first byte of the key. So we can do this step by step. And we know the input, and we can just guess the key. Because, okay, trying to guess the entire encryption key is crazy, but trying to guess one byte of an encryption key, there are only 256 different guesses. You can literally just try them all. A factor of 256 is not a big deal. And after the S box, what we're going to do is we're going to look at the Hamming weight of the output. And this works beautifully. We control the input. We're just going to send random input bytes, but it means that we can basically control the groups of the Hamming weights. And what we're going to do, we're going to say, okay, we're going to guess all 256 possible bytes that correspond to all of our random inputs. And we're going to work out the Hamming weights that should be in the traces. And we're just going to see which one fits the best. So just the master plan is just for every key guess, so all 256 key guesses, byte by byte, remember. For every input, we calculate what the Hamming weight should be. We compare it with the actual leakage. And at the end, we just pick whichever group fitted the best. And this is all getting woolly, and it's like, I'm pretty sure I promised there would not be theory. This is something called correlation power analysis. And I could go on and try and explain this with actual math, and actually so people might understand it. But the thing is, what are you going to do next? If you're trying to do side channel analysis, are you going to go and implement this algorithm? You're going to try and write this? I mean, I don't know about you, but I'm lazy. We're both lazy. We are not going to do this. We're going to go to Google, we're going to type side channel analysis, and we're going to use some software that someone else wrote. And that's exactly what we did. Thanks so much to Case. We're using open source software called JLSCA, basically because it's fast. It does CPA. It does all kinds of fancier attacks that we don't care about. And it also runs fast on that cheap network that you used because you're connecting it to this flaky hardware. But there's one more ingredient here. So we have this open source software, you know, the laptop you have lying around, your Arduino Nano, maybe some resistors for the shunt resistors. And it all sounds pretty great. So you send these random inputs to the processor. You take these power measurements. And you take these pairs of the input and the corresponding power measurement, and instead of thinking about all this best fit, first routes at AES, you just say, JLSCA, here is some data, give me the keys. And it just gives you the keys. As you'll see in a bit, it's really that simple. Except this. You need an oscilloscope. So you can see, again here, I hope, please, this is the best pattern. Again, this is software AES. You will see it everywhere if you start looking. But you need an oscilloscope. And how expensive are oscilloscopes? Well, you might have access to one. But if we start thinking about kind of bored attackers who are sitting at home, then are they going to have an oscilloscope lying around? Maybe not. I mean, a good question is, how many of you have an oscilloscope at home? Maybe a cheap Rigol? How many of you have access to an oscilloscope of some kind? Okay, so, you know, that's a reasonable amount of the room, but not everyone. The thing is, if you start asking side channel experts, you know, what kind of oscilloscope you should get, then they start saying, oh, you should buy the LaCroix we have in the lab. No. And realistically, even these Rigol scopes, which are lovely and cheap and work great, they're still several €100. It's a lot of money. The great news is other people before us have already encountered this problem and tried to fix it. So Colonel Flynn developed the Chip Whisperer, which is wonderful hardware. And you have our ex-colleague Rafa, who showed that you can do this with a cheap USB oscilloscope, like the one pictured here. And that works great, but it's still quite a bit of money if you're just bored and you just kind of want to randomly try this out. And finally, this is the future maybe. It's the Chip Whisperer Nano. It's a cheaper version of the Chip Whisperer. It's nice because it has a target built in. And on the right side, you can see it even has a shunt resistor built in. But it's $50 still, and it's still not actually available. And as Albert would say, that is a lot of beer. So we can solve this very easily. This can't be this expensive. I mean, if we look back at the Chip Whisperer Nano, it has all these components on it. What are all these things on this PCB? So let's just build a scope of our own. And it turns out we don't know anything about electronics. And also, we don't know how to solder things. We can kind of bodge together the power cuts. So it quickly turned into, of course, what's the minimum effort thing you can do to hack things together? And it turns out, what do you need from an oscilloscope to do this side channel analysis? Well, you need some way of trigger, so to tell the oscilloscope when to actually start measuring. But that can just be some kind of random GPIO pin. You need some way to actually collect the measurements. It's just an analog digital converter. And you need some RAM to put measurements in. And it turns out you can pick pretty much any cheap microcontroller on the market, and it will have all three of these things. Because we make poor life choices, what we went for is the Atmel Xmega. It's the successor to the Mega chip on the Arduino Nano. It's great. It has USB 2. It has a 12-bit ADC. It has 2 mega samples a second, which to us seems like a lot. Until you go to AliExpress and you start looking for boards based on this. And it turns out the chip may be $2.50, but you know, chips with the boards with the chip on it are like $50. Because apparently no one uses this chip. So of course the next step is learn PCB design and actually develop our own board. And we did. We called it the horoscope. It's not going to be the focus today, but it's just a random breakout board, basically. This is what happens when you need a random microcontroller. You pick a random microcontroller, and it turns out, oh, you know, all these cheap breakout boards are available for everything except the incredibly poor choice of microcontroller that we made. And now I'm going to hopefully hand over to Albert, who will talk about my terrible mistakes.
Okay, so Alyssa just gave us a bit of an introduction on side channel attacks. And she also introduced basically the hardware that we designed and built. So when we sent this off to get the board manufactured, so our prototype came back, and we had our first problem. So it turns out we actually, mixed up the data lines. So we switched them around. So to solve that problem, we have a USB crosslink cable. Right. So, but we did this basically so we could test the board and then find out if there were any other problems. All right. So after we built the crosslink cable, we can actually tackle some real problems. So it turns out one of our biggest problems is that we're actually planning to sample well below the Nyquist frequency. So the Nano runs at 16 megahertz, and our ADC samples at 2 megahertz. So clearly, this is not enough. You're not going to get a sample every nano clock cycle. And in fact, if you listen to the experts, we're actually sampling 32 times too slow. So how are we going to solve this? Well, maybe we can just take more measurements. And we can also have a look at the datasheet. So, this is apart from the datasheet, it says it has 12-bit resolution, and it does up to 2 million samples per second. So it turns out that this 2 million samples per second is just a suggestion. You can also try sampling at 4 megasamples per second, or perhaps 8, which didn't work. Okay, so we're back to more traces. Additionally, we don't have an analog front end. So typically, an oscilloscope will actually have a piece of analog electronics, basically an amplifier, in front of its ADC. So that sounds like work, so we're not going to do it. And we're probably going to compensate by taking more traces. Additionally, there's this 50 hertz signal, which sometimes comes through, which shows up as a DC offset. And we have all these resolution problems. Also, the USB being directly on the chip actually gives us more noise. And basically, we're going to solve that by taking more traces. So I'm pretty sure you noticed a pattern there. I said, take more traces. So when we were prototyping the software, we accidentally misconfigured the ADC. And this is a trace we recovered. And I was actually already pretty happy with this because, if I take 100 of these measurements and average them, what we actually see is these AES rounds coming out. What you can also do is not misconfigure the ADC. Okay, so we now have an oscilloscope. So let's actually try to actually do some acquisitions with this. So as Alyssa already explained, but just to recap, we have a PC which controls both the oscilloscope and the targets. And the PC sends messages to the targets, and basically the oscilloscope measures the power usage. And there's also this thing called the trigger. So our real-world setup actually looks something like this. We have our Arduino Nano up here, which runs our AES, and we have the horoscope down here, and we have some resistors over here. Okay, so this triggering thing, we mentioned it, but what does it mean? So basically the question is, when does the oscilloscope know when to measure? We don't actually have enough SRAM to actually basically to keep it running all the time. So we need some way to synchronize basically this Arduino Nano with our oscilloscope. So then the question is basically, what is the last thing we control before this AES happens? And that's actually us sending the input. So the triggering plan for the horoscope is something like this. First, the PC sends a command to the scope, to ARM, to get ready for this measurement. And then a GPIO input pin hopefully turns high. And basically, directly after that, the measurements will start. So what we're going to do is we connect the scope GPIO input pin to the receive pin on the Nano. So basically, when the Nano receives a command, we can actually trigger. And if we were to build a Python script to actually tie that all together, a loop iteration would look something like this. We would start our loop iteration. We would send most of the input. After we send most of the input, we tell the oscilloscope to get ready. And then when it's ready, we send the last byte of input. And this will do two things simultaneously. So first of all, the scope will see this byte coming around on the serial line, and it will start measuring. And additionally, because the target sees this last byte arriving, it will actually perform the AES. Okay, so after that, we basically save all our data, we save the power trace, and we start again. And we acquire a lot of inputs. So to collect these traces, we need a lot of inputs. And we just need to make sure that either the first or the last round is in view. And we need to make sure that we actually sample with a reasonably high sample speed. And we need to make sure that, as we'll see later, we need a little bit of a margin before and after the round. So if we go back to the traces Alyssa already showed us, which turns out were actually made with the horoscope, we can actually see these rounds of AES, and we probably want to collect either here, if we're taking from the input, or maybe from the output over there. So then we start the acquisition, and then we wait, in our case, for about an hour and a half. And then we have all these measurements which we can process. So we don't actually have time to do it live. So we're actually going to use some data we already collected previously. So we take these measurements, and we look at them, and it turns out they are shit. Why are they shit? Well, they are something called misaligned. So we plotted two of these power measurements on top of each other, and you can see that these peaks don't really align nicely. They're not on top of each other. And this means basically in both measurements, two operations the same operation doesn't happen at the same moment in time. So if we look at what the experts say about this, is they say if you do your statistics and you have well-aligned traces, you will get this very nice sharp spikes. However, if you have misaligned traces and you do the same statistics, you don't get these sharp spikes, you get this bump, this spread out bump. And additionally, that bump might not actually come out of this background noise level. So basically, we need to align them. So thankfully, JOSCA can align them for us. So we did. And what we see actually is that we aligned on the end of the AES. And what we see is that even though we aligned part of the trace, some of these other parts are no longer aligned. So this part is aligned, but let's say the end is not aligned and the beginning is not aligned. So this could be either because our oscilloscope is just really bad, or it could be because the Arduino AES library is not time constant. Okay, so if we now do a little bit of statistics, just to prove that the alignment we did is actually useful, we can actually do some statistics on the output we receive. So before we did this alignment, we actually see that we just have this noise band, and basically you maybe see some peaks coming out of it, but it's not very convincing. And after we do this alignment, what we see is that the noise band is a lot smaller compared to these very, very sharp peaks we see at the end. And in fact, we can actually see the output bytes coming out of the AES one by one. Okay, so let's do a demo and actually now try to recover some keys. So I'm now going to start using a Jupyter Notebook. Does everyone know what a Jupyter Notebook is? Yeah, I see some people nodding. Okay, so it's basically a way to interactively run code. So here we basically we open our measurements, and what we see is that these traces are not nicely aligned as we predicted. So what we do is we run a little bit of alignment code down here, and it now is aligning all these traces we collected. And what we see is that, as we said, the end part is now very nicely aligned, but this region over here is not, and neither is this part here. But that's not really a problem for us because we're actually only interested in this region. Okay. So if we now do some statistics on the output, again, we actually see that we actually get these very, very nice spikes. So we're actually reasonably confident that if we run an attack, we might actually we might actually recover the key. So we're now running the attack. And basically, what we see is this. So we're now focusing. We're now focusing on like the last input byte, so the last key byte. And what we see is that Julia SCA has taken all these guesses and did the statistics on them. And it's ordered all these guesses, which it calls candidates, basically by the score. And what we see is that the highest ranked key candidate has a score of 0.5, and basically all the others have a score of, let's say, 0.25. Which means that there's actually a very large difference between this correctly ranked first candidates and everything below it. So this actually tells us with a reasonable confidence that we've actually recovered the correct key byte. So we can then also do it for the second to last key bytes, for instance, and we see pretty much the same story. The correct key byte is on top, and it has a score of 0.5, and all the others, again, something like around 0.2. Okay, so we can also actually represent what it's showing us slightly differently. So what we have here is a plot that shows how these scores evolve over time as we give more traces. So on the x-axis, we have the number of traces that the JOSCA has processed, and on the y-axis, we have basically the score for all these key candidates. And what we see is that when JOSCA hasn't processed enough of these traces, basically all these key candidates are in this noise band. But as we keep adding traces, what we see is that this noise band still exists, but one of these key guesses the score starts to increase and increase and increase. And this is that correct key candidate I was talking about. Now, what we could also do is basically collect all these plots together and do this for all keys, but that would give a really messy picture. So what we can also do is make a plot which is called the rank evolution. So basically, this means you're asking, what is the position? What is the position of my correct key candidate between all these other candidates? So this is something you can only do if you actually have the key already. So what you see is that when you don't give it enough traces, all these keys have basically a more or less random rank. But as you give more traces, they all start to float to the top, start to float to rank 0. And after you've collected a certain amount of traces, all the key ranks are 0. And this means you've basically recovered the entire key. So with that, we go back to the presentation. Okay, so we gave this demo. Now we've recovered this key using our homemade oscilloscope. But how bad is it really? So it turns out that if we buy this cheap oscilloscope of AliExpress for about $70, we can actually recover the key in approximately 1,500 measurements. And with the horoscope, it may differ a bit, but it's at least an order of magnitude more. On the other hand, it's also a lot cheaper. So yeah. So basically what we see is that we can make all these mistakes, and we actually still get these attacks to work. So how many mistakes can you make so that it stops working? So originally we worked on some prototypes which someone else made for a different reason, and the silk screen, so basically the writing next to the pins had an off by 1. So everyone told us that the ADC on the Xmega was really bad. So we took a measurement like this, and okay, it's bad, but we can still sort of see these rounds of AES, right? But because the silk screen was an off by 1, we hadn't actually connected the pins. So what you're seeing here is a measurement we made without actually connecting the pins to the ADC. However, if you take 1,000 of those measurements and average them with no alignment, you can actually see these rounds of AES. again, with the pins not connected. So unfortunately for us, we didn't actually recover the key in that case because we required that many traces. But already the fact that you can see these rounds appearing, basically when you haven't even connected up the wires, is rather worrying. All right, so basically for these side channel attacks, there's strength in numbers. And basically these attacks require that the noise from the system is overcome. And we can actually reduce this noise by basically taking more traces. However, sometimes the way the protocol is written, for instance, doesn't allow you to do this. All right, so enough about all this boring theory part. Let's talk a little bit about fault injection before we finish up, because I already see everyone going a bit tired of all this theory. So it turns out the horoscope can actually sort of power the Arduino Nano. So the Nano normally works at 5 volts, and the Xmega GPIO pins can provide 3.2 volts. Clearly, we can actually power it some of the time. Yeah, so how do we connect it for fault injection? What we do is basically that power cut we had before, we connect basically the entire port C GPIO pins 0 through 7, we connect it to the VCC line of the target. And then basically by toggling these GPIO pins really quickly, we can actually induce faults into the computations. So we have faults, and actually we could now actually perform differential fault analysis, which basically means you inject faults into running AES, and then you look at some of these faulty outputs, and if you have enough of good faulty outputs, you can recover the key. Okay, so we can do all those things to the Arduino Nano from this horoscope, but what could you do about it? Well, the first thing you could do about it is you could look at your threat model and try to identify if you can come up with some way in which basically these attacks really don't matter. So for instance, by changing the protocol. There are also some other basic steps you could do to protect your device, and basically I think one of the easiest steps is to use some hardware that actually has built-in countermeasures already. But then even if you do that, I think at some point it would be a great idea if you actually looked at the power usage of these devices and actually tried to ascertain how much they leak, using either a real oscilloscope or perhaps the chip whisperer. So just to conclude, these hardware attacks are a lot cheaper than even we thought. And side channel analysis is something you can do at home, and you should just give it a go. So we'd like to give a special thanks to Kees for actually writing JLSCA. We'd also like to thank Rafa for really motivating us and saying it wouldn't work. We'd like to thank Ilya for letting us steal his pictures, and we also did a workshop, and we'd like also to thank those attendees for all the feedback they gave us. So because you're in this room, we also have a bit of homework for you, which we expect to have back tomorrow. We have a GitHub repository. We will provide the power traces and the JOSCA notebook, and you should be able to get the key. We've also provided the schematics and all the source code we need. And we're actually also hoping that someone will port all of this basically to an STM32, an STM32 blue pill, so we can actually do SCA for even cheaper and also less work. So with that, if you have any questions, you can ask them either now or in the upcoming days, because we'll still be around.
And maybe, of course, we can't show you a whole feature demo here, but we have a chip whisperer with us, and we have all this equipment with us. If you'd like to come and play, we'll be here all week. So please do.
That's the spirit. I like that. Any questions?
I didn't quite understand the part where you said you could see traces and you didn't even connect the pins or something like that. I didn't catch that.
Yeah, so it turns out the pins, I started, that's fine. I'm going the wrong way, sorry. So because the pins were mislabeled, we connected them basically to the pins next to the pins we thought we connected. So we didn't actually connect the pins, but because they were still so close together, they still somehow, I don't know, electromagnetically coupled, or there was some leach effect, or I don't know.
And maybe one thing you don't see here is we don't do a scale, right? So the Y scale is just kind of scaled to fit what's there. And it turns out what you're seeing here is way lower signal levels than what we've shown in the other graphs, but it's still there.
Yeah. Yeah, so also, as Alyssa's pointing out, we actually really don't know what this voltage level is because we haven't calibrated it because we don't care. Any other questions?
Thanks again, Albert.
Thank you.
We conclude the day here, at least the technical presentation part. There was a German night. I encourage everybody to take part in that. Mingle with other researchers and learn us about it. For some of you, see it for track 2 in this room, track 1 in the other room, as today.
But I really mean it. I mean, if you want to play with this stuff, we really want to see more people doing this stuff on random hardware, better understanding. Come talk to us.